First of all, good afternoon to everybody. And before starting, I would like to really thank Professor Cristina Basso for the kind invitation. And believe me, it's really a pleasure and an honor to present to the Padova University something related to cardiomyopathies. It's true that in the title I put the ARVC because it's one of the topics in which I am involved. But in reality, and I apologize from the beginning, I mean, my presentation will be very simple in the sense that, as in the title, I would like to show you the possible application of atomic force microscopy. And I will present some data also for cells from cancer cells, other kind of cardiomyopathy also, in the sense that atomic force microscopy can be a tool for checking the mechanical behavior in general of cells. And then at the end, I will show you also something about tissue. And as the Professor Cristina Basso said, I have to disclose that, in fact, my wife is Luisa Mestroni, and she is here in Colorado, and she has been working with cardiomyopathy for all her life. And kind of around 15 years ago already, time is flying very fast, one night we were discussing at dinner, wife and husband maybe should discuss something else. But anyway, we were discussing about this slide in which you can see on the right side two different cells. She was preparing the slide for a presentation, and we were discussing about the cytoskeleton of the two cells, and you can see that it's completely different. So Luisa was saying from, and I'm not want to criticize, no, from a doctor, from a medical point of view, she said, well, it's obvious that the cytoskeleton is different, and so the cells cannot function properly. And I asked her how much either softer or weaker is the cytoskeleton, and she said, who knows? So since all my life I work with mechanical properties, but just to let you know, I mean, I was working with the tiles of the shuttle, so ceramic material, that kind of stuff, completely different. But I said, well, maybe we can also measure the mechanical properties of the cells. And so I start thinking how to do it. And then going through the literature and so on, I discovered, for instance, and this, I think it's a very important data. So the mechanical forces inside cells are much faster than the biomechanical, so pathway and so on. So mechanical forces move around 30 meters per second compared to 1-2 millimeters per second of biochemical signal. So it's becoming clear. This was data around 2006, so let's say 20 years ago. So it's becoming very clear that mechanical forces are important in several diseases, one of which, of course, is also the ARVC. So I start working on that. And so let me just briefly tell you what is the atomic force microscopy. In theory, it's a very simple device, even though, believe me, it's not so simple. But anyway, there is you see, it's like a blind guy that is checking with a stick the surface of something. And in particular, of course, the stick of the blind is very small. There is a cantilever here, and you can change the cantilever based on what you want, whatever you want to measure. So, but the most important part is that at the end of the cantilever, there is a tip, and there are different kinds of tips. You can have a pyramidal tip, you can have a small sphere, There are also very, very sharp tips. So it depends what you want to measure. At the end, you see the atomic force microscopy is not a huge device. You can put it on a bench, on a table. But of course, what is very important is that you can measure these mechanical properties, and we will see about cells and so on, in fluid. So really in the biological system, you can, of course, check the temperature. So the cells will be at the right temperature in the biophysical fluid or whatever. And so in this sense, it's a very peculiar device that allows to get a lot of data, you will see. But again, I have to stress the point that it's not a silver bullet. It will show you something, it will give you some data, and then of course you have to check also with other methods, immunofluorescence or whatever, just to be sure what you have seen. But anyway, you will see that in the years we understood that it was possible to get several data, you will see. So first of all, you can do morphology of the cells. On the left here, you can see what really the AFM is giving you. And here is there is a software, of course, who give you the 3D representation from this data collected with the AFM and the stick, the tip, of course. And you can see the morphology of the cells. You can get something else, for instance. In the case we check some fibroblasts from patients with Danon disease, and we have seen that there were, as expected, some lumps inside the cells, and you can use also the AFM to check, let's say, the rugosity of these cells. So how many lumps there are, how big they are. And you can see this is a control cells, and this is the Danon cells. And you can see clearly that there are the lumps, and you can measure how many there are, and so on. Another case actually related to ARVC was a work on PK. Actually, this was on HL1 cells, and we had a PKP2 mutation. And again, this is the control. These are the PKP2 cells. And you can see again with the AFM and 3D representation, we have seen that there were, again, this is not done on, of course, and in fact, these lumps are lumps of actin inside the cytoskeleton. So even though the mutation was related to the desmosome with the PKP2, even the actin network was in some way destroyed, let's say, or affected by the mutation. So the possibility with the AFM, let's say this is, I'm not saying is the most simple, but so you can get some results also with the morphology of the cells. Another data that you can get, and for instance, this was done with the HeLa, not the cancer cells, but you can do what with all of cells, is to measure the height of the cells. And this was at the beginning of our works, and we treated the HeLa cells, this is the control, with the two chemical compounds that are affecting either the actin, so affecting the component of the cytoskeleton. So cytokalasin D, who is targeting the actin filaments, and the nocodazole that is targeting the tubulin. And so we went and we measure how the cell change their shape due to, as I said, either the cytokalasin or the tubulin or the nocodazole. And what is interesting from here is that what we have seen, are not the data I will show you later, is that if you target with the nocodazole the cell, and so targeting the tubulin, the cell became also stiffer. And then going through the literature, I've seen that nocodazole is used as a chemical compound also to try to treat cancer cells. In that case, they are using because it's reducing the possibility for the metastasis to duplicate. But it can be also interesting to, maybe you know, and I'm sure you know very well, that metastases are much softer than normal cells. So unfortunately, they can go around our body very easily. But the nocodazole, since he is making the cells stiffer, can be also a good way of reducing the possibility for the cells to move around our body. Another possible application of the AFM, so AFM, of course, is the acronym for atomic force microscopy, okay, is to measure the, what is called, when you measure mechanical properties, it's called force spectroscopy in general. So in general, you can use the atomic force microscopy to measure also the mechanical properties of single molecule. We will see that you can apply the AFM to single molecule, then to the whole cell, and then also to tissue. In this case, is single molecule. Again, you can use either a tip, a sharp tip like this one, or a small ball that can be functionalized. There are different way of using, but anyway, what you get is this one, that in some way you attach a protein to a substrate, and then you attach the other, the end of the protein, let's say, to the tip, and then you start taking up the cantilever and measuring the force during the unfolding of the protein. And normally what you get is this kind of curve, very peculiar. It's called the Shaw curve. And from this one, you can get several information. For instance, we use this method, but I mean, people around the world are using for, of course, every kind of protein, let's say. Just something to relate it again to ARVC is that we apply this method to the titin. You know very well, I mean, the very long, maybe the longest protein that we have in the body, and very important for the mechanical properties of the heart. And with Professor Granzier in Arizona, we focus on this part of the titin, the N2B US part that is very important, even though it's very small, but it's very important for the mechanical properties of the titin. And so what we have done in a nutshell, because it's a long story, but anyway, you see, this is the real behavior of the unfolding of the protein, and this is the control. What you can have from this kind of curve are three different data. So what is called the contour length, that is the whole length of the protein when it is completely unfolded, the persistent length, and the unfolding force. Now, as I said, it's a long story. I don't want to go into details, but the persistence length, it's very important. And sorry to tell you what it is, maybe you know very well, but I mean, so what is the persistent length? Well, when I have to talk with my student, I think that the most simple way of explaining it's the spaghetti. So if you take a spaghetti that is uncooked and it will be very difficult to bend the spaghetti, okay, unless you break it. So the spaghetti stay linear. If it's cooked, of course, it can bend very easily. So the persistent length, in a nutshell, is the length of a protein, the length of a protein before bending. So, for instance, a rope has a very short persistent length because it can bend very easily. So it's a very important data for the proteins. What we have seen is that using two kinds of phosphorylation in the N2B US part, this phosphorylation and this one, the ERK2, there is a change, a clear change in persistent length, for instance, compared to the control, but also there is a difference between these two phosphorylation behavior. So you can measure a lot of properties of single protein, okay, so single molecule as it is called, but let's move to the cells. So you can do also what is called the force spectroscopy of single cell. So again, in a nutshell, what we are doing normally, I mean, around the world, let's say, there are people for this kind of test, there are people using a sharp tip of a spherical tip. For my idea is that, and the idea of other people, is that the spherical tip is better because, of course, you are pushing on a larger surface compared to a sharp tip. But anyway, in general, what you are doing is that you approach with the AFM, the cantilever and the ball, the cell, you start pushing the cell, and then you retract the cantilever. Now, it's quite obvious that when you are retracting the cantilever, there will be a time in which the sphere is still attached to the cell. There is an adhesion, okay? So you will have a behavior that will give you some data that we will discuss just in the next slide. That is this one. So the curve that you obtain, the data that you obtain, is a plot of the force, the force that the AFM it's applying to the cell against the deformation of the movement of the AFM. And you see, this is the loading curve, okay? And then there is the unloading. But as you can see here, the unloading has also a part just below here because the sphere is still attached to the cells. And we will discuss later, these data are also, I think, very, very important for cardiomyopathies and so on, and ARVC also in particular. So from the loading part of the curve, okay, this is just an example of two loading parts, you can get the elasticity of the cells. Now, in engineering way of talking about elasticity, we call it the Young modulus. So the Young modulus, it's indicated as a capital E. You see it's written here, Young modulus, is the elasticity of the cells. The higher is the Young modulus, the stiffer is the material. Okay, just to give you an idea, I mean, talking about something else, steel has a Young modulus of 200 gigapascal, whatever, gigapascal. Aluminum, that is much softer, has only 65 gigapascal. Here in with the cells, of course, we are talking about much, much lower order of magnitude, lower elasticity. But anyway, remember that the higher the Young modulus, the stiffer is the material. And let me show you just a few seconds of the real behavior. I hope that it's working. Let's see. Okay, so you see this dark one is the cantilever of the AFM. You see the cells that are beating. The cantilever is approaching the cells. You see this small spot is the tip just below. And of course, there is a laser that takes all the measurement. Now you see the sphere here. And so it's measuring it's going on top of the cells. And at that point, it's measuring, it's approaching, so it's pushing the cells, and then it's getting up for the unloading part. So, for instance, we measured the elasticity many times, but let me show you just one example. So this is the elasticity of 3 mutation of the lamin mutation, even though, and we were, so, you know, I will explain later, but so there are, can you hear me?
Gaetano, si sente tutto l'audio, Gaetano, per favore.
Yes, we can hear you.
Oh, okay, okay. So in this case, we tested 3 lamin mutation. It's you see here the E192, 195, 161. Luisa, my wife, told me that, so she gave me, of course, the cells. Oh yes, I forgot to tell. I mean, the collaboration is going quite well because, of course, being an engineer, I need somebody providing the cells with the mutation or whatever. And so apart of the cancer cell and so on that I got from other group of research, with Luisa, the collaboration, and especially with the group here in Denver, but also with the group in Padova, there is a stream of cells with different mutation and so on. So in this case, we check and we knew that the outcome for the patient are different when there are these 3 mutations, and we check the elasticity of these cells compared to the control and the wild type. And effectively, there are, so you see that the cells are stiffer, and also the 3 mutation, the outcome of the 3 mutation based on the elasticity is different. So what we have done, for instance, later, is to try, if it's possible, a rescue of this 3 mutation based on the fact that a P38 inhibitor at that time, and it looks it was working very well now, was one possibility to have a rescue. And in fact, if you see here, this is the data of the control, and the 3 mutation, especially the 192, the worst, let's say, as far as the elasticity was concerned, were rescued by the use of P38. So a way of applying the atomic force microscopy in this case, for instance, is to measure the mechanical properties, the elasticity, and see if with some kind of drugs you can get a rescue. And another, so let's move to another data. If you remember, I told you that during the test, we have the unloading part of the curve, and the sphere remain in contact with the cells for a period of time. And this area, so I enlarge this part, this area below give you, again, several data. So one is, of course, the whole area. The whole area is what is called the work of adhesion. So how much the sphere can stay in contact with the cell, but you have also the maximum force to remove the sphere from the cell, the position of this maximum force, and then there are other two interesting data here. So the first part here, these small drops are the breaking of the bonding, of course, the protein of membrane. This long part of, let's say flat parts, are the rupture of what are called the nanotubes. So long tethers that are coming out from the cells and are related to the communication between cells. Now, the test that I described before, as I said, was made with a sphere in contact with the cells. Of course, you can do also cell-to-cell contact. I will show you also some data that we have done. So you can have a cell attached to the cantilever, go and approach the cells that is on the substrate, and then see, of course, the cell-cell adhesion instead of the sphere-cell adhesion. In any case, the behavior is always the same. There will be this area providing the data that I told you before. Here are what I said. So the rupture are adhesion proteins. So there are short breaking forces. And then there is the long tethers, the nanotube that are breaking. So again, for the three mutations that I showed you before, with the lamine mutation, we measure also the adhesion work. And again, you see, there is if you remember, the elasticity was different, but the cells became stiffer. In this case, the adhesion work, even though, and that was a point that really concerned me or bothered me at the beginning, was but why a mutation in the lamine that you know very well, it's just around the nucleus. In some way, it's also affecting the adhesion work. But in reality, as you can see, there is a clear decrease in the adhesion work of the three mutations compared to, as usual, control and wild type. And again, we tried the rescue with the P38, and as I showed you before. And in fact, also in this case, even though it's not perfect, the rescue, but there is a clear rescue, especially for the 192 and 195. So again, you can check also with the adhesion work if there is possible a rescue. Now, if you do cell-cell adhesion, as I told you, and we try to do, for instance, the adhesion between fibroblasts, cardiofibroblasts, of course. With in this case, I'm showing you only the data for the 192 mutation. And if you, of course, there is a software, if you check all the rupture, here we are talking about the rupture, so only the protein of the membrane proteins, there is a clear difference between the control and the 192, especially around 60 piconewton. There is a lack, you see, for the control, there is a lot of rupture in this area. There is a lack of rupture in around the 60 piconewton. That, by the way, are more or less the data for the caderins. So you can also find out which kind of proteins are, in this case, the membrane proteins are affected during the adhesion test. You can do the same for the tethers, for the nanotube, for the long nanotubes, and again, control against the 192. There is a difference here that it's possible to explain also with the mechanical properties of long tethers coming out from the cell membrane. So again, work of adhesion or the adhesion behavior, let's say, can provide also some interesting data related to cardiomyopathies, for instance, but not only. Another, so let's move to another point, is that the cells are viscoelastic material, are puffy material. So it's, well, let's say from an engineering point of view, it's clear that the cell must have a viscoelastic behavior. So there is, so viscoelastic, it's clearly means that there is a part that is behaving elastically, but there is also, and it's obvious, I mean, the cells is plenty of fluid. There is also a part of the cells that is behaving in a viscous mode, okay? Think of a container, okay? Plenty of liquid in which you put a golf ball, for instance, and then you start moving, okay, shaking the container. Now, based on the viscosity of the liquid inside, of course, the golf ball will move, with different speed. Okay, if the liquid inside is very dense, is very viscous, the sphere will go, even though you steer very quickly, the sphere will move slower than if the fluid is very fluid. Okay, so anyway, in engineering way, you can describe this behavior with two data. Again, I don't want to go in a lot of details, but you will see in the next slide that they can be also important. So there is one data that, of course, is related to the elastic part. It's called the storage modulus. And there is a part that is related to the viscous part. It's called the loss modulus. Normally, they are indicated with G1 and G2. Okay. So why I told you they can be important? Well, again, going through the literature, what I found is that typically for a normal, healthy, let's say, cell, this ratio between loss and storage modulus must be around 0.1, 0.2. And if there is a pathological state, this ratio will change. So again, measuring this data can give you, as usual, I told you, I mean, it's not a silver bullet. It's just a data in the sense of research, but can give you some ideas of the behavior of the cells. For instance, and what you are doing with the AFM, it's you are, again, approaching the cells, staying there for normally 30, 60 seconds on the cell and measuring what's going on. But again, I mean, there is a protocol. So, for instance, here, again, data that we got from the HeLa, but we got also, and we publish also for cardiac fibroblast with the 3 mutation that I showed you before. It doesn't really matter. So, you see, this is the G1, the elastic modulus, the storage modulus. And again, if you remember, I told you, for the HeLa, we use the cytochalasin D and the nocodazole. This is the control. You see, here are the data that show you that the nocodazole is, with the nocodazole, the cell is becoming a lot stiffer. You see, it's much higher, the elastic part. So it's much stiffer. With the cytochalasin, it's much softer compared to the control. And this is the part of the viscous part. Again, if you enlarge this part, you see Again, I don't want to go to the details, but normally what you have for the loss part, for the viscous part, in changing the frequency, not the hertz, the frequency in which you are testing the cells, normally you see two maximum and a minimum. But the position of this, of course, the value of the maximum, but the position also of the two maximum and the ratio, you see how it changed between the nocodazole. The first maximum is much higher than the second one. With cytocalasine, the first is much lower than the second one. And of course, they are also moving from, as the frequency is concerned, can give you again some results how the distribution of the protein inside the cytoskeleton, again, talking actin, tubulin, intermediate filaments, are behaving in the cells during the viscoelastic test. So again, you can get also viscoelasticity data, and then again, moving also with the years, working with my wife and other groups, we start thinking of measuring the beating force and frequency. Of course, in this case, we are talking only about cardiomyocytes. And for instance, here you can have a difference between control and after propanol. But this, for instance, is real data, let's say, that we got for the progeria just recently. We are publishing the paper just now. And as you can see, I mean, the progeria it's completely different, no? The beating frequency and also force of beating. And of course, I mean, the test is just going on top of the cell with the cantilever, with the AFM cantilever, with the tip, and staying there for, again, 30 or 60 seconds normally, and measuring what's going on. And again, so for the progeria, you see, again, against control and wild type, there is a difference in frequency, of course, as we have seen, and also a lower force of beating. And then I realized that probably you know very well this one, the Poincaré plot. It's something that in cardiology is used also to define the AKG plot, let's say. And so you can take the data that we have seen before, this data, plot them in this kind of Poincaré plot, as it's called, and the data should stay in an elliptical area, let's say, and you see these two data, SD1, SD2, can give you also an idea of the arrhythmogenic, let's say, behavior of the cells. We did also, as I said, it's not a silver bullet, so at this point we connected this data with also the calcium flux, let's say. And as you can see, I mean, wild type and control are very smooth, let's say, and the progeria beating, it's completely different. Oh, sorry, no, this is not the beating, this is the calcium.
Sorry, Orfeo,
yeah.
sorry to interrupt you, just 3 minutes because I have meeting time, okay?
Yeah, no. sorry. Okay. I will finish. I'm very close to finishing. So it's different, and you can check this one. So this is the last, also the last year of working. You can get data, similar data, especially for the young modulus. So the behavior of tissue, and again, this is what really you get from the AFM. This is the reconstruction of the cells, and you can get, you see, every pixel can be a measure of the young modulus, of the elasticity of the tissue. You can get 60,000 force curves per scan, and the scan is 100 micron by 100 micron. And then you can isolate it, for instance, the fibrosis. And that, let me, so just show you this one. What we have found, and again, we are publishing now, is that normally the method to detect the fibrosis are this Picro series thread and the second harmonic imaging. But with the AFM, we show that the AFM is more sophisticated and can see differences in the young modulus, so in the elasticity of the tissue, better than both the two systems. And the reason is that the two systems that I mentioned before can see only the, as is written here, only collagen 1 and 2, while the AFM, even though cannot tell you if it's collagen 1, 2, 3, or whatever, can measure all the stiffness, so taking into consideration also other protein that can be, of course, part of the fibrosis. And the last part, this is not my work, I'm thinking of doing because I found very interesting, even the name, it's something very new, it's called unroofing. So unroofing is taking away the roof of the house. And it's true, I mean, what they are doing is they are going inside the cell with a very thin tip of the AFM, and then you see you can get incredibly high resolution. This is part of the actin, incredibly high resolution inside the cytoskeleton, inside the cells. But as I said, this is something that I just found, and it's fascinating. I will try to do it in the future. And so summarizing, you see, you can get morphology, you can get single molecule force spectroscopy, elasticity, adhesion work, viscoelasticity, beating frequency and force, and tissue analysis, especially for the fibrosis. And that's it. Thank you so much, as I said, for the invitation and the possibility to show you what we are doing.